Okay. First of all, I would like to introduce you to my material. Well, not mine, but it's a composite material, so it will be different to the previously mentioned. With continuous glass fibers, and the matrix was polypropylene. The manufacturing technique was the hot press technique, so I will tell you a little bit about it, how it works. There is a foil, and between them there are fibers. And they are supplied in a continuous way, and then we produce a material, and then we cut it into layers. And then we put these layers one on another, and we obtain a material at the dimensions that we would like to get. So here's the shape of the material, and here is the microstructure. So, well, you can see that there are like more darker and lighter colors, which means that the lighter and here these colors are fibers, and between them there is a matrix. In a perfect material, we would have it totally even, but due to the manufacturing technique, we obtained some parts where we didn't have so much fibers, and there was a lot of matrix, which is not really good for us because this is a weaker part of the material. But to be honest, it works, and things are produced using this technique, and they're really good, so it was worth it to analyze. Okay. During my research procedure, we analyzed 5 different types of dimensions. I will show them later, which gave us different ratios of maximum to normal stress and strain during bending. Like we have bending in our material. And thanks to this, we have different types of cracks, either translaminar or interlaminar. Both of them are very dangerous, especially in composite materials, as the first is growing, and then suddenly we have a crack without saying, hello, I'm going to crack. It's just cracks, and we have very catastrophic, we can have very catastrophic results. So in my analysis, I analyzed just strain, not stress, which also is very important in composites. And in order to get the result, I used digital image correlation. And then I knew where exactly I have, or how big strain I have where. I analyzed both the first crack and the further analysis what happens to the material next. So we will see some pictures in next figures. Of course, I had some, it was certain the results, so I had to use some filters to obtain more accurate results. Both the surface filter and the time filter, because we know that the strain value doesn't go like this, just it wasn't perfect. I analyzed the epsilon x, y, and the which are normal strains, and shear strain. I just showed 2 different notations because in general in composites we use the void notation, but in bone there is epsilon x, y, and xy, so it's just the same. Okay. So the first material was the frequently bending of the very thin specimen with 2 millimeters. And I was sure that I'm going to obtain pure normal, pure crack due to normal strain. I analyzed 5 specimens for each dimension, so we have here the graph, and the purple line, the dotted line is in here, which I'm going to show you now. Oh, thank you. Okay, the 2 doesn't matter. The first point is the point where just before the crack, like milliseconds between the sub and fiber. The specimen had a shape of an arc, and it didn't seem that it's going to crack in a second. But analyzing the strain in here, we can see that the epsilon x, so the normal strain along the fibers, because we have the fibers along the specimen everywhere here, was 0.022. So it was the value when this crack, when the fibers crack, actually, because fibers are the thing that keeps it together. So when the fibers crack, then the material cracks. And just in the next step, because it's like 30 milliseconds after, there was crack already, and we could see that there are straight lines in here, and just this part was an arc. So we knew that the material is can no longer be used. I analyzed also what happens next, so it was just moving on, and the force was dropping, and there was nothing to do with the material anymore. I don't know, we could make out of this a bicycle, and I wouldn't like to ride on this bicycle anymore. Okay. Okay, another version was the three-point bending of a very thick specimen. Sorry, it should be 20 millimeters in here. So it was very thick, and I was sure that I'm going to have interlaminar failure due to shear strain. Okay. This specimen, and as you can see, the epsilon X or Y are actually 0 in the location when the crack appeared in here. And on this specimen as well, we can see any information that we're going to have a catastrophe in a moment. But it happened because, as you can see, there was drop, not so big, not as in the previous version, but also we can see that there was a lowered volume. But what's interesting, the force started to grow up. But the reason is very easy. Instead of shearing, we started to have compression because the like here, we have compression in here. So, but after that, something like this happens. So I and you can see, but there is the lamination like every 2 millimeters or something. So between the layers, we started to have a lamination which was not visible before. Okay. Another, I think that is the most interesting, actually, maybe it's interesting, because for composites, they often suggest that due to local stress strains, something could happen. So they suggest to analyze 4-point bending. Well, it's an option, of course. But what happened in my situation just after this beautiful specimen, you can see that there is no visible crack, you can't see anything. Just on the colorful pictures, you can see that the angle is almost 2 degrees. So you can see that it's going to crack. And of course it cracked. And like milliseconds later, here you can see a crack. And then and these are just 2 different parts. And after that, we have complete failure of the material. Okay. The 4-point bending of the same dimensions, but a thicker specimen, showed us that the specimen divided into 2 parts. Like very similar situation like the previous version, so I think it's not worth it to analyze it anymore. But what happened in here? Would you check? Okay, here just after the first crack, in the middle, like we predicted, we had a lamination, and then we have like it's divided into halves, and then like on this graph you can see that the first started to grow up again, and after that we had it cracked into another parts, like this part cracked into 2 halves, and this other 2 halves, and so on until there was nothing left in this material. And this one is my completely favorite one because it was like something in the middle. I was wondering if I'm going to have totally normal strain and then translaminar or shear strain and interlaminar. So I analyzed. And what happened in the first condition? The translaminar fracture, as you can see, we can't predict the failure, but analyzing the strain, we know that the epsilon X is 16. In the clean specimen, we had 22, but here it's a little bit lower, but we have theta almost 1, so complex strain state, let's call it. So it's cracked in here. Okay, here at the end of the specimen, we had fibers cracked in here and in here, because also in composite materials, so we need to analyze that the fibers can be subjected to buckling, so it's not it's worse to compress them than to subject them to tension. But it wouldn't be anything interesting up to now. But this next one. And I had analyzed 5 specimens of each type. So the first one was a translaminar fracture, but this one was interlaminar fracture. And here, like this location, sign us here, the specimen started to be subject to have interlaminar fracture. And at the end, as you can see here, the fibers are just in here, and I had lamination in my material. And another one was even more interesting because I had both translaminar and interlaminar fracture, and they happen in milliseconds between them. Here, like in here, we have a very big epsilon x coming from compression. And here we have buckling of the fibers. And in the same time here, I started to have lamination. So like milliseconds between each other, I had 2 different types of fracture. Yeah, and here we can see here we have nothing less. It's totally different to this place. And here we have a crack due to the lamination. And this is at the end, so that you can see that the specimen is completely destroyed. Okay, so summing up a lot of data, sorry for so many data, but here is the most important part, like these 2 last columns. I had 5 different normal stress to shear stress ratios. So the first one was normal. Here I know it would be shear, but there were some in the middle. And this is my favorite one, 24, where I had both translaminar, interlaminar, and connection of those 2 types. So and here I just for formality analyzed the pictures of the distribution of shear and molar strength. I guess that you know how it works, but I would like to say that well, it was according to my observations were according to the theoretical values. So everything seemed to be very fine. Yeah, and now it works. Okay, so summing up to the conclusions, because the conclusions are always like most worthy. First, the most important is that the digital image correlation reveals cracks that we can see with an armed eye. The specimens seemed totally normal, and we would think that they're going to work and work and work. But the strengths using the digital image correlation showed that in a second we're going to have a crack, so it's not safe anymore. I summed up all of those specimens. The 3-point bending, there was a sudden fracture, as I suspected it would be. In the thin specimen where I was I thought that I will both have the lamination. There was the lamination, so everything happened according to plan. I did not get 4-point bending. Both of them, I had the lamination and then division into next specimens and so on and so on. And the 3-point bending, there were different types of failure. And well, I didn't tell you why before it happened, because there were different specimens from different materials. And as I showed you in the beginning, the material had uneven distribution of fibers. So sometimes it was more even, sometimes less even. And if there is uneven distribution of fibers, then when there was just polypropylene, of course it would crack in there. And when there were more fibers in an even way, the material could analyze and could stand more. So it's really important to analyze the microstructure, and it's also what's happening, and here the digital image correlation really helps us because we could predict this information using it, the digital image correlation, and without the interpersonalizing force, we would have nothing because the force would be still okay, but this strain, just local strain would lead us to really catastrophic results. Thank you very much. If you have any questions, I would like to